The night sky you know will not exist in a billion years. Our solar system is a masterpiece in motion, and we are about to witness its next act. In this journey across an almost unimaginable timescale, we will explore 15 profound transformations that will reshape our cosmic home. You will gain a sweeping vision of our ultimate place in a universe where nothing is permanent. We will see Earth's oceans vanish, watch as Mars may briefly become habitable, and discover if our solar system could capture a wandering rogue planet. From the slow brightening of our sun to the distant thawing of frozen worlds, this is the future written in the stars. What do you think will be the most surprising change to our cosmic neighborhood? That slow burning clock starts ticking for Earth long before the sun becomes a true monster. The first and most profound change we will witness is the relentless brightening of our own star. Think of it not as a sudden explosion, but as the steady turning of a cosmic dial. Every second, the sun converts millions of tons of hydrogen into helium deep within its core. This process is not perfectly efficient, and as helium ash accumulates, the core must contract and grow hotter to maintain the nuclear fires. This, in turn, causes the entire star to glow more fiercely. The numbers are staggering yet deceptively slow, a 10% increase in brightness every billion years. To us living our brief lives, this is an imperceptible shift. But over the immense timescales we are exploring, it is the ultimate game changer, the master variable that will rewrite the rules for every planet. This increasing luminosity directly redefines the solar system's habitable zone, that theoretical band where a world can support liquid water on its surface. As the sun grows brighter, this comfortable belt steadily marches outward. Earth, currently nestled in the sweet spot, will one day find itself on the inner edge, and then squarely within a region of growing solar intensity. The extra energy pouring onto our planet will begin to accelerate the evaporation of our oceans, pumping vast amounts of water vapor, a potent greenhouse gas, into the atmosphere. This creates a feedback loop, a climatic trap where more heat leads to more vapor, which traps even more heat. Scientists see this as the likely trigger for a runaway greenhouse effect, a point of no return where Earth's climate could eventually mirror the scorching, inhospitable conditions found on Venus today. This transformation won't happen tomorrow or even in a million years, but it is the first and most inevitable domino to fall, setting the stage for the planetary upheavals to come. Our blue planet will not remain blue. That relentless increase in solar brightness we discussed sets in motion a chain of events so profound it will erase the defining feature of our world, the vast global oceans that have existed for billions of years. This is the second great change, the end of Earth's liquid water. Think of it not as a sudden boiling, but as a slow, unstoppable leak on a planetary scale. Over hundreds of millions of years, as global temperatures climb, the water cycle will accelerate into overdrive. More evaporation from warming seas will pump immense amounts of water vapor into the air. And here lies the cruel twist: water vapor is itself a powerful greenhouse gas. This creates a feedback loop with no off switch, a moist greenhouse effect where more heat creates more vapor, which traps more heat, which creates even more vapor. The atmosphere will grow thick and hot, a global sauna. Eventually, this humid blanket will reach high into the stratosphere, where intense ultraviolet light from the sun will begin to tear the water molecules apart. The lighter hydrogen atoms, freed from their bonds, will then be lost to space forever, a slow but irreversible bleed of our planet's most vital resource. The heavier oxygen will remain, but the water itself is gone for good. Planetary models suggest this is a point of no return. The great oceans will shrink, retreating first to the deepest basins and finally vanishing entirely, leaving behind vast, salt-crusted deserts under a blazing sky. What remains may be only trace pockets, perhaps hidden in shadowed polar regions or deep underground. This marks the definitive closing of a chapter, the end of Earth's long tenure as a life-nurturing world for any biology we would recognize. It is a sobering reminder that planetary habitability is not a permanent condition, but a temporary, beautiful phase. And as Earth loses its atmosphere and water, another world will begin to feel the sun's growing warmth in a very different way, setting the stage for a dramatic planetary reversal. While Earth's oceans fade into memory, a new world may briefly step into the light. This is the third profound change, a cosmic irony written in the slow shift of starlight. As our sun brightens and pushes the habitable zone outward, Mars will find itself, for the first time in billions of years, in a position to potentially host liquid water on its surface. Think of it as a second spring arriving incredibly late. In perhaps 500 million to a billion years, the increased solar energy reaching the red planet could trigger a monumental thaw. Today, Mars holds immense reserves of water ice locked in its polar caps and buried in its soil, alongside frozen carbon dioxide. As temperatures rise, these ices would begin to sublimate, releasing water vapor and carbon dioxide gas into the thin atmosphere. This process could create a powerful greenhouse effect of its own, thickening the air and trapping more heat, which in turn accelerates the melting. It is a positive feedback loop that could, for a time, transform Mars. River valleys carved in a wet ancient past might once again flow with water. Transient lakes could shimmer under a pinkish sky. For a window of time that is brief on a galactic scale but long by human measure, Mars could become a temperate, if fragile, world. Yet this potential spring is haunted by a fundamental flaw. Mars lacks a global magnetic field like Earth's, a protective shield that deflects the erosive force of the solar wind. Any atmosphere that reforms would be slowly but surely stripped away, particle by particle, back into the void. Furthermore, the sun's relentless brightening does not pause. The very same process that gifts Mars this temporary warmth will eventually overheat it, pushing the habitable zone even farther out. So Mars may not be a permanent new home, but rather a way station, a glimpse of what could have been. It forces us to see planetary habitability not as a fixed address, but as a wave that passes through the solar system, briefly touching one world before moving on to the next. And as that wave of warmth continues its outward journey, it will begin to awaken kingdoms of ice at the very edge of our knowledge. Far beyond the future of Mars lies a realm of perpetual winter, but even here, the sun's slow brightening will write a new chapter. The fourth great transformation in our solar system's story is the gradual thawing of the distant ice giants' moons. Consider Uranus and Neptune, sentinels in the frigid outer dark, circled by frozen worlds like Triton, Titania, and Oberon. For billions of years, these moons have existed in a state of profound cryogenic sleep, their surfaces a tapestry of water ice, frozen nitrogen, and methane as hard as rock. The additional solar energy delivered over the next billion years will be a mere whisper at this distance, but in the economy of deep space, even a whisper can have power. The temperature may rise by only a few critical degrees, yet that could be enough to initiate a slow-motion resurrection. On Neptune's captured moon Triton, with its bizarre cantaloupe-like terrain and faint nitrogen geysers, this subtle warming could transform the surface. Vast plains of frozen nitrogen will begin to sublimate, turning directly from solid to gas, thickening Triton's wispy atmosphere into something more substantial. We might see its cryovolcanic plumes grow more active, painting temporary dark streaks across its icy canvas. Around Uranus, larger moons like Titania and Oberon harbor secrets beneath their crusts, likely deep subsurface oceans kept liquid by internal heat and antifreeze compounds. A warmer surface environment, even marginally so, could alter the delicate balance of their icy shells, potentially triggering new cracks, resurfacing events, or shifts in the hidden seas below. They will not become tropical paradises. They will remain bitterly cold, hostile worlds, but they will change, shifting from static ice sculptures into slightly more dynamic and geologically active bodies. This slow awakening at the solar system's edge is a profound reminder that no world is an untouched museum piece. Every corner of our cosmic neighborhood is connected to the fate of our central star. And as this gentle warmth penetrates the outer darkness, it will also begin to stir the ancient, pristine material left over from the solar system's birth, the frozen denizens of the Kuiper Belt. The deep freeze at the solar system's edge is not eternal. The fifth monumental shift will be a subtle but pervasive thaw in the Kuiper Belt, that vast reservoir of icy remnants beyond Neptune. Here in the perpetual twilight, worlds like Pluto, Eris, Haumea, and Makemake exist as frozen time capsules, their surfaces a brittle crust of methane, nitrogen, and carbon monoxide ice. For eons, these volatile compounds have remained locked in solid form, stable only in the profound cold. But as the sun's output slowly climbs over the next billion years, even this distant realm will feel a change. The temperature may rise by only a handful of degrees, yet in the razor-thin atmosphere of deep space, that is all it takes. These exotic ices will not melt into liquids, they will sublimate, turning directly from a solid into a tenuous gas. Imagine Pluto's vast heart-shaped glacier, Sputnik Planitia, not as a static plain of frozen nitrogen, but as a slowly exhaling landscape. This process could gift these dwarf planets with transient, hazy atmospheres that bloom into existence when their orbits bring them slightly closer to the sun, only to collapse and snow back onto the surface as frost during their long, cold winters. This seasonal dance will become far more dramatic than anything we see today. The constant resurfacing will change their appearance, brightening some areas and darkening others, potentially triggering new geological activity as the loss of surface material alters the pressure supporting the terrain below. It is a profound revelation. These distant outposts are not inert museum pieces. They are dynamic worlds, and their slow awakening is a direct response to the changing heartbeat of our star. This great melt at the frontier signifies that no part of our solar system is immune to the passage of cosmic time. And as these distant ices stir, the delicate gravitational balance that orchestrates the entire system from the center to the edge will itself begin to feel the strain. Gravity's clockwork never stops ticking. The sixth fundamental change is a slow, imperceptible drift in the very architecture of our solar system, driven by the relentless pull of orbital resonances and planetary migration. We often picture the planets as fixed on perfect, eternal tracks, but reality is far more dynamic. Each world exerts a tiny gravitational tug on the others, and over hundreds of millions of years, these gentle nudges accumulate into a profound dance. Think of it as a grand, celestial ballet performed in ultra-slow motion, where a single step takes an entire geological era. The most significant dancers are the giants Jupiter and Saturn. Their immense gravity shapes the entire system, and their complex gravitational relationship, a kind of rhythmic push and pull, continues to evolve. They are likely migrating outward ever so slowly, moving farther from the sun as they exchange energy with countless smaller objects in the asteroid belt and the Kuiper Belt. This movement is minuscule, perhaps a few meters per year, but multiply that by 1 billion years and the shift becomes substantial. This outward journey of the giants subtly alters the gravitational landscape. It changes the locations of stability zones and resonance points, those delicate regions where an object's orbital period is a precise fraction of another's, like a harmonious note in a cosmic chord. These resonances can act as both protectors and disruptors. For example, Jupiter currently shepherds the asteroid belt, its gravity preventing the formation of another planet and occasionally flinging debris inward. As Jupiter's orbit gradually changes, so too do these zones of influence. This could make the inner solar system slightly more or less susceptible to showers of asteroids and comets over epic timescales, altering the long-term impact risk for any remaining worlds. It is a reminder that stability in astronomy is a relative term, a temporary balance in an endless gravitational conversation. And as the giant planets continue their stately migration, their movement sends ripples through the populations of smaller bodies that share their realm, setting the stage for a different kind of celestial rearrangement. The gravitational tide set in motion by the giants will sculpt even the rocky debris between the worlds. Our seventh great change involves the slow, systematic depletion and dynamical cooling of the asteroid belt. This vast ring of rubble between Mars and Jupiter is often called a failed planet, a relic of the solar system's violent construction phase. But it is not a static museum. It is a population in constant, slow-motion flux, and its future is one of increasing order and quiet. Two subtle but relentless forces are at work here. The first is the gravitational influence of Jupiter, the solar system's grand architect. Its immense pull creates chaotic resonances, zones where an asteroid's orbital rhythm syncs up with the giant planets in a way that gives it periodic, powerful kicks. Over millions of orbits, these kicks can add up, altering an asteroid's path just enough to send it careening inward toward the Sun or outward into the void. The second force is far more delicate, a thermal nudge known as the Yarkovsky effect. As an asteroid spins, its sunlit side heats up and later radiates that heat away as infrared energy as it rotates into darkness. This tiny emission of photons acts like a minuscule thruster, imparting a gentle push. Over eons, this thermal drift can significantly change an asteroid's orbit, slowly walking it into one of Jupiter's gravitational resonance zones where it is then swiftly ejected. The combined effect of these processes is a great cosmic filtration. Smaller asteroids, which are more susceptible to the Yarkovsky push, will be cleared away most efficiently. They will either be flung from the solar system entirely, fall into the Sun, or, on rare occasions, be redirected on a collision course with a planet. What will remain after a billion years of this filtering? A sparser, more orderly belt. The surviving asteroids will predominantly be those on stable, circular orbits with low inclinations, paths that keep them far from Jupiter's most disruptive influences. Astronomers call this a dynamically cold population. The belt will transition from a tumultuous construction site to a quieter, more settled neighborhood. This gradual clearing is a key part of the solar system's long-term tidying process. It reduces, but crucially does not eliminate, the background risk of catastrophic impacts on planets like Earth. The story of bombardment is not over, however, for a far more unpredictable source of cosmic projectiles still lurks in the deep freeze. The calm of our future asteroid belt will be punctuated by visitors from a much darker frontier. This eighth great change connects our fate to the galaxy itself through the slow stirring of the Oort cloud. Envision a vast spherical shell of trillions of icy fragments, stretching nearly halfway to the next star. This is not a tight belt, but a diffuse and distant halo, the solar system's ultimate attic, filled with pristine leftovers from our formation. These objects are so far out that they barely feel the sun's grip, and this makes them susceptible to a far grander force, the gentle gravitational tide of the Milky Way galaxy itself. As our sun orbits the galactic center, it bobs up and down through the dense plane of the disk roughly every 30 to 40 million years. Each passage is like wading through a slightly stronger current, and that galactic tide can nudge these loosely held Oort cloud objects, altering their orbits just enough to send them falling inward. Even more dramatic are the rare, close encounters with other stars drifting through our neighborhood. A passing star, even at a distance of a light year, can act like a gravitational plow, shaking loose a shower of these icy bodies. The result is a cosmic schedule of bombardment that operates on timescales far beyond human history. We will experience a persistent, slow drizzle of long-period comets from the cloud, each one taking thousands or even millions of years to complete a single orbit. Occasionally, after a particularly close stellar flyby, that drizzle could turn into a downpour, a brief but intense comet shower raining into the inner solar system. While these events pose a long-term hazard, they are also cosmic delivery services. Each comet is a frozen time capsule, carrying water ice and complex organic compounds, the very ingredients that likely seeded the early Earth. So even a billion years from now, as the inner planets bake under a brighter sun, these primordial messengers will still arrive, a faint echo of the solar system's violent and creative birth. This eternal perturbation reminds us that our cosmic neighborhood is not an island. Our destiny is gently tugged by the immense, slow dance of the galaxy. Deep within a planet, a quiet engine is running down. The ninth profound transformation is the slow death of planetary magnetic fields, the invisible shields that have guarded worlds for eons. This is not a sudden collapse, but the ultimate consequence of a planet's internal heat slowly bleeding away into space. Think of Earth's core as a powerful, self-sustaining dynamo, a churning ocean of molten iron and nickel that generates our global magnetic field. This protective bubble, the magnetosphere, deflects the constant torrent of charged particles from the sun, the solar wind, and cosmic rays from deep space. It is what keeps our atmosphere from being slowly eroded away. Yet this engine has a finite fuel supply, the primordial heat from our planet's formation, and the ongoing heat released as the inner core slowly solidifies. Over the next billion years, as the core continues to cool, the vigorous convection that powers the dynamo will begin to falter. The magnetic field will weaken, becoming patchy and unstable before fading entirely. We can see the ghost of this future on Mars today, a world whose internal dynamo stopped billions of years ago, leaving it with only a wisp of an atmosphere and a surface scoured by radiation. For Earth, the loss of its magnetic shield will be the final, definitive act in the story of its habitability. It will occur long after the oceans have vanished, but it will seal the planet's fate. The remaining thin atmosphere will be exposed and stripped away by the solar wind, particle by particle, leaving the barren surface bathed in unfiltered stellar and cosmic radiation. This internal cooling is the planetary equivalent of a heartbeat growing faint and still, a transition from a vibrant, protected world to a geologically quiet and exposed relic. Even the mighty gas giants are not immune to this slow change. The intense magnetic fields of Jupiter and Saturn are generated by the incredible pressures within their layers of metallic hydrogen, an exotic, electrically conductive form of matter. As these planets radiate their internal heat over trillions of years, their internal structures will also evolve, potentially leading to a gradual weakening of their immense magnetic shields, though on timescales far longer than a mere billion years. This quiet internal change, however, has a direct and measurable effect on a planet's most fundamental rhythm, the steady spin of its day. The steady slowing of Earth's spin is a clock you cannot hear ticking. This 10th great change, the lengthening of our day and the tidal locking of the moon, is a story of gravitational friction written across eons. Our planet's rotation is not a constant. It is a resource being slowly spent in a cosmic transaction with its companion. The moon's gravity creates the ocean tides, but those bulges of water do not sit perfectly beneath the moon. Earth's spin drags them slightly ahead. This misalignment pulls on the moon, boosting it into a higher, slower orbit, while the moon pulls back, acting as a gentle but relentless brake on Earth's rotation. The result is a gradual transfer of Earth's rotational energy to the moon's orbital motion. Within the next billion years, this process will have added a noticeable amount to the length of our day. A day on Earth will no longer be 24 hours, it will stretch longer, perhaps by over an hour. This is not merely a change to our clocks, it reshapes fundamental planetary rhythms. A slower rotation weakens the Coriolis force, the effect that shapes our global wind patterns and ocean currents. Our weather systems, our jet streams, even the stability of our axial tilt could become more susceptible to perturbation over immense timescales. And as the moon retreats, its apparent size in our sky shrinks. The perfect cosmic coincidence that gives us total solar eclipses where the moon just barely covers the sun will end. Future observers, if any exist, will see only annular eclipses, rings of fire where the smaller moon is silhouetted against a larger solar disk. This dance leads toward an ultimate, frozen embrace called tidal locking, where Earth would present one face permanently to the moon, just as the moon already does to us. That final state lies tens of billions of years in the future, far beyond even our billion-year view, but the journey toward it is already underway. A slow, graceful deceleration set in motion the moment the moon formed. Yet for other moons in the solar system, gravity's embrace is not a slow dance but a countdown to destruction. Gravity's embrace is not always a gentle dance. For some moons, it is a slow march toward oblivion, and this 11th transformation reveals the divergent destinies of two captured worlds, Phobos and Triton. Their stories show how tidal forces act as a relentless sculptor, capable of both creation and destruction on a cosmic scale. First, consider the small, irregular moon of Mars, Phobos. It orbits incredibly close to its planet, so close that Martian gravity is actually pulling it closer with each passing century. Tidal interactions are sapping its orbital energy, causing it to spiral inward. Within the next 50 million years, a mere blink in our billion-year view, Phobos will cross a critical boundary known as the Roche limit. This is the point where a planet's tidal forces exceed the gravitational pull holding a moon together. As Phobos crosses this line, the difference in gravity between the side facing Mars and the side facing away will become overwhelming. The moon will not simply crash, it will be systematically pulled apart, shredded into a cloud of rubble. For a time, Mars will wear a brilliant, transient ring system, a fleeting memorial to its former companion before the debris eventually rains down onto the rust-colored surface. Far across the solar system, a much larger moon is on a similar, though slower, path. Neptune's captured moon Triton, an icy world larger than Pluto, orbits in the wrong direction, a retrograde path that betrays its origins as a kidnapped Kuiper Belt object. This backward motion creates intense tidal friction with Neptune, and like Phobos, Triton is slowly decaying in its orbit. Over the next billion years, this decay will continue. While a direct collision with Neptune is possible, the more likely fate is a repeat of the Phobos story, but on a colossal scale. Triton too will approach and cross Neptune's Roche limit. When it does, the resulting disintegration would create a ring system of staggering beauty and complexity, one that would utterly dwarf the iconic rings of Saturn. Imagine Neptune, already a deep azure jewel, encircled by a broad, luminous band of ice and dust, a temporary crown formed from the remains of its greatest moon. These two stories, one of a small inner moon and one of a giant outer captive, share the same breathtaking conclusion: destruction giving birth to ephemeral art. They remind us that the celestial architecture we see today is not permanent, but a single frame in a long film of gravitational evolution. And if moons can be torn apart to form rings, what fate awaits a planet that finds itself wandering alone between the stars? The aftermath of a moon's destruction is not an end but a transformation. Following the tidal shredding of Phobos, Mars will gain a spectacular new feature, a ring system of its own. This is the 12th great change, a celestial makeover born from violent loss. Initially, the debris from the shattered moon will form a dense, chaotic disk, a swirling storm of rock and dust encircling the planet's equator. Over several million years, collisions and gravitational interactions will sculpt this chaos into order, spreading the material into a coherent, flat ring. Unlike the brilliant, icy rings of Saturn, a Martian ring would be composed of dark, rocky material, the same stuff that makes up Phobos itself. It would appear as a subtle, dusky band against the blackness of space, a somber yet beautiful halo for the red planet. From the surface, any future observer would see this ring arching across the sky, a constant, elegant reminder of the moon that once was. But like all things in this evolving system, it would be a temporary masterpiece. Ring particles would slowly spiral inward due to the faint drag of Mars's thin upper atmosphere, burning up as faint meteors. Others might clump together under their own gravity, accreting into new, tiny moonlets, beginning the cycle anew. This ephemeral ring underscores a profound truth. The adornments of planets are not permanent decorations. They are fleeting sculptures shaped by gravity and time, testaments to an ongoing story of construction, destruction, and rebirth right in our own cosmic backyard. And while one world gains a ring from a destroyed companion, our solar system as a whole remains open to the possibility of welcoming a stranger from the interstellar void. Our solar system's borders are not closed. The 13th monumental shift could see our family adopt a new member, a rogue planet captured from the interstellar void. Astronomers estimate our galaxy alone may harbor billions of these nomads, worlds violently ejected from their birth systems in gravitational upheavals, now condemned to drift forever in the freezing darkness between the stars. Over the immense span of 1 billion years, as our sun journeys around the galaxy, a close encounter with one of these lonely wanderers becomes not just possible, but statistically likely. If a rogue planet passes near the outer reaches of our sun's gravitational influence, it could be snared, its kinetic energy traded for a permanent, if irregular, new home. The most probable outcome is a distant and wildly elliptical orbit, a looping path that takes it from the inner Oort cloud out to staggering distances, a ghostly addition to our solar system's farthest frontier. This captured world would be a frozen time capsule, an ice-shrouded body that never felt the warmth of a star, preserving in its depths the pristine chemistry of the early solar nebula. Its arrival, however, would be anything but gentle. The gravitational disturbance of a new, substantial mass in these distant regions would act like a boulder dropped into a still pond. It would shake up the delicate orbital ballet of countless Kuiper Belt objects and Oort cloud comets, scattering some into interstellar space and nudging others onto long, falling trajectories toward the inner solar system. This could initiate a new era of comet showers, a lasting echo of its dramatic adoption. This possibility transforms our view of the solar system from a static family portrait into an open, evolving community, forever subject to the chance encounters of our galactic voyage. And as we contemplate new worlds being captured from the cold, we must also turn our gaze to a world that will be utterly transformed by heat, a celestial body destined for a spectacular and total metamorphosis. While some worlds fade into geological slumber, others are reborn in fire and ice. This 14th great change is the endless surface renewal of geologically active moons, a testament to the power of external energy in a cooling solar system. Take Jupiter's moon Io, a world caught in a perpetual gravitational tug of war between Jupiter and the neighboring moons Europa and Ganymede. This constant, rhythmic flexing generates immense tidal heat within Io's interior, powering a global volcanic circus unlike anything else we know. Its yellow and orange landscape, painted with sulfur and silicate lava, is not a permanent face. It is a temporary mask. The relentless volcanic activity will completely repave Io's entire surface countless times over the next billion years, erasing impact craters almost as quickly as they form. It is a world in a state of constant, violent creation. Far colder but no less dynamic, Saturn's tiny moon Enceladus offers a different kind of renewal. Here, tidal heating from Saturn maintains a global subsurface ocean of liquid water beneath an icy shell. At its south pole, immense fissures known as tiger stripes vent this ocean's contents into space in spectacular cryovolcanic plumes. These plumes of water vapor and ice crystals continuously snow back onto the surface, refreshing it with a bright, clean coat, making Enceladus one of the most reflective bodies in the solar system. This process is a window into a hidden, potentially habitable sea, and it will continue for eons. Even Neptune's captured moon Triton, on its long journey toward a possible disintegration, may experience a final burst of activity. As the sun's faint additional warmth seeps into its nitrogen ice crust, the pressure in its subsurface reservoirs could increase, leading to more frequent and powerful geysers, a last gasp of dynamism before a dramatic transformation. This ongoing geological theater presents a stark contrast. Worlds like Mercury and our own moon, their internal heat long since dissipated, are frozen in time, their surfaces ancient archives of impacts. But moons like Io and Enceladus remain vibrant, their faces ever-changing because they are plugged into the gravitational power outlets of their giant planets. This dichotomy shows us that planetary aging is not a uniform process. Some worlds remain geologically young forever, animated by forces beyond themselves. Yet all these magnificent processes, from volcanic repaving to icy plumes, are merely supporting acts for the final, ultimate transformation that awaits our entire system, a change that will redefine the very meaning of home. The final act of our billion-year story begins with a change in the light itself. That steady, reliable yellow disk we have known since Earth's dawn will start to lose its familiar hue, swelling into a deeper, more ominous orange. This is the 15th and most profound transformation, the prelude to our sun's metamorphosis into a red giant. While the full, cataclysmic expansion lies billions of years beyond our current view, the final billion years of our journey set the irreversible gears in motion. Deep within the sun's core, the silent accumulation of helium ash reaches a critical threshold. The core, no longer able to sustain stable hydrogen fusion as efficiently, contracts and grows even hotter. This forces the star's outer layers to respond, beginning a slow but unstoppable inflation. The sun will evolve off the main sequence, the stable, adult phase of its life that has lasted for over 9 billion years, and enter its subgiant stage. From the perspective of any remaining inner worlds, the change in the sky will be palpable. The sun will appear noticeably larger, a great ruddy orb casting a warmer, dimmer, yet more pervasive glow. This shift in color and size is not merely an aesthetic change, it is a fundamental signal. The internal stellar processes that will eventually lead to the engulfment of Mercury and Venus, and the utter transformation of Earth's remains, become locked in during this era. This prelude is the ultimate turning point, the closing of the long, stable chapter that allowed our solar system to coalesce, planets to form, and for life, against all cosmic odds, to flicker into existence on one small world. It frames our entire present reality not as a permanent condition, but as a fleeting, beautiful moment in the immense biography of a star. Every ocean that ever existed, every mountain that ever rose, every story that was ever told, unfolded under the light of a star that was, all along, slowly changing. This long view forces a perspective of both profound humility and wonder, for it reveals that we are living in the golden age of our solar system, a temporary masterpiece of stability in an endless flow of cosmic change. This grand cosmic story unfolds on a timescale that defies human intuition. Our entire recorded history, from the first cities to the present day, is less than a blink in the narrative we have just witnessed. To contemplate a billion years is to step outside ourselves, to see our moment not as the center of the story, but as a precious, fleeting scene in an epic far greater than our own. This exercise in deep time is not a prediction for humanity, for our species will likely be transformed beyond recognition or gone entirely long before these events come to pass. Instead, it is an exercise in understanding the universe's fundamental machinery. The principles of stellar physics, orbital mechanics, and planetary geology we have explored will proceed with a beautiful, indifferent certainty, whether anyone is here to witness them or not. There is a profound humility in that realization, but also a powerful expansion of perspective. It stretches our sense of scale, connecting the warmth of the sun on your skin today to the slow, inevitable brightening that will one day bake the continents. By studying this impossibly distant future, we gain a clearer lens through which to view our own past. The violent migrations of giant planets help explain the strange architecture of our solar system today. The runaway greenhouse effect on future Earth sheds light on the harsh climate of Venus. This knowledge transforms the planets and moons from static points of light in the sky into dynamic characters, each with its own origin, struggles, and destiny. They become part of a story with a beginning, a long, complex middle, and a definite end. This cosmic context does not diminish our world, it elevates it. It frames our present era, this sliver of stability between ice ages and infernos, as a rare and extraordinary chapter. It encourages a deep cherishing of this pale blue dot, with its vast oceans and protective sky while we have it. And as we look outward, this understanding travels with us. It informs how we interpret the thousands of exoplanets we are discovering around other stars, allowing us to read their possible histories and futures in the light of our own system's grand biography. We are, for a brief moment, the universe becoming aware of itself, capable of tracing the arc of its own story from a fiery birth to a distant, cold conclusion. That awareness is perhaps the most human thing of all, a spark of consciousness in the vast, slow dark. Our journey through deep time reveals a universe where permanence is an illusion, a grand stage where every world, from the sun-baked rocks of Mercury to the icy frontiers of the Oort cloud, is a character in motion. We have traced the threads of a future written in the laws of physics, watching as oceans vanish, rings form from shattered moons, and distant ice slowly stirs. This tapestry of change, woven across a billion years, shows us a solar system not as a finished portrait, but as a single frame in an endless film of transformation. The stability we cherish today is a fleeting gift, a temporary calm in an epic narrative of cosmic evolution. Yet there is a profound comfort in this knowledge, for it means the same principles we use to understand a falling apple or the orbit of a satellite also allow us to forecast the fate of worlds. We are not passive observers of a static sky. We are participants in a story of discovery, using the light of reason to illuminate the darkness of the far future. This ability to look backward to our origins and forward to our ultimate destiny is one of humanity's most remarkable gifts. It transforms our perspective, encouraging a deep and humble awe for the dynamic, ever-changing universe we are privileged to call home, if only for a cosmic instant. If this voyage through time resonated with you, we would love to hear which transformation captivated your imagination the most. Share your thoughts in the comments below and subscribe to continue exploring the grand mysteries waiting just beyond the edge of our understanding. The story is far from over, and there are always new horizons to discover.